Hi. This is example, manual calculation example for the second chapter. This example is the one in the book, chapter 217. So there is a list given us to here saying that this CVS corresponds to constant voltage source. So let me open that a bit. So in this chapter we have seen ideal elements. Ideal elements are the theoretical elements, but in practice we might not exactly the same ideal elements available in the market. So what is available in the market for a constant DC source, constant VS, constant voltage source? When we say constant voltage source, sometimes we call it DC source, DC voltage source. So some of these examples, batteries, this type of elements, batteries. So the ones that you buy in the market for your telephone, there is a battery, and most common batteries are the 2AA 1.5 volts, and there are 9 volts batteries as well available. Car batteries, for example, 12 volts. These are all batteries. These are all constant voltage source. Now these practical constant voltage sources, in terms of ideal element, it is composed like that. An ideal voltage source, DC, that is ideal, and a resistor. So A and B. So this is now, let me change the color. So what we've got here is, that's the practical battery, and this is the corresponding ideal elements included model of this. Now what is asked here in this question, there is a list here. They are saying there is an element, there is a circuit here, and they measure this current. So that means this current is related with this part of the circuit. And we've got VS as well. So what is asked here, what's the value of this? So let me change the color once more. What is this ideal DC voltage source voltage, what it is? The second, what is the value of this resistor? So by using this list here, they are asking this calculation of those two. Now also it says here, so you can plot this, so I'm not going to do this here, I'm going to skip that one. It says in B, construct a circuit model of the practical source that is valid for IS in between this. So that means we're going to use this part, and for this part it is asked to us what is the values of these ideal elements. Based on the equation of the line plotted in A, use an ideal voltage source in series with an ideal resistor. Now I'm not going to do it by the plot, but I'm going to show you how I'm going to calculate those two values. Now if you consider now, let me clear this a bit, make it a bit better. So I'm going to consider there is an element, or there is a circuit here. Let's say this circuit. I'll make it a bit better. I don't know what it is, but what I know is this. I know this current, that IS. So if I connect this to this one, so this IS, I know this I, as I write it right away. And I know the VS as well. So let me come to this one. So this VS and this IS. And let me complete this connection as well. So this is like that, and this is like that. So I'm going to write now with Kirchhoff voltage law for this loop. Let's say I'm going to show this as VI. You might consider V input, and this is RI. You can consider it internal resistance, we call it. Now, if I write Kirchhoff voltage law for this loop, what's going to be? It's going to be like that. IS is the same as this resistance current, so voltage of this resistance is RI multiplied IS plus VS is equal to, that's going to be minus VI. If I put it on the right hand side, it's going to be plus, isn't it? So this is VI. So this is Kirchhoff voltage law equation for this loop. So I will be using this equation now. So this IS, VS, so those two, we've got the values for that, isn't it? So what it says here, if IS equal to 0, so this I'm going to apply now. IS equal to 0, that term is going to, so this is VRA, isn't it? Resistance voltage, and VS, IS. If IS is equal to 0, the first line, so that term is going to be 0. Conclusion, VS is equal VI. So VS is 75. So I found this VI value. So this ideal voltage, source voltage, is 75 volts. So I think 75 volts, isn't that? Voltage says. And then how I'm going to calculate the RA is easy. So use the second line. Second line tells us VS is going to be 60 and IS is 75 milliamp. So RI times 75 milliamp, 75, 10 to the power minus 3, plus VS is 60, isn't it? The second line. 60 is equal, I already calculated VI is 75. So what this is going to end up with, RI is equal. So if I move this 60 to the right hand side, it's going to be 15, isn't it? 15. If I divide it with this, 75, 10 to the power minus 3. So that's going to be, gives you 5, 1 over 5. And this is equal to 1 over 5, 10 to the power 3. So that means 200 ohms there. So I found this value as well, 200 ohm. So for these two, you do the calculation. You see, you're going to end up with the same RI. So that means for this 3, that is 3. You'll do it your own. you're going to get the same result. Vi value is equal to is going to be equal to 200 ohms. Okay. So that means in practice, when you got a source, the corresponding ideal element model of this practical source is like that, and we found these values. Now let's get some conclusion out of this. One of the conclusion is this. I'm going to redraw this one here. Make it a bit better. There's one source and then one resistor under the connection. So this is what I said, the model is this. Accumulator, let's say car accumulator is something like that, isn't it? In the car you see those, so there is, okay, there's one pole here, another terminal here, that's the accumulator. Okay. Now what we are saying, this is practical, and this is theoretical model. So that is Vi, this is Ri. So the ideal independent voltage source for us is this, isn't it? Theoretical. We are saying this is 5 volts. If we say 5 volts here, that is the ideal. Whatever you connect here, that voltage does not change. It is independent voltage source. Now, how this practical element quality becomes almost equal to ideal element. So to answer to that question, if this Ri value as small as possible, ideal case, if Ri is equal to 0, that means Vi is going to be directly independent voltage source, isn't it? So the ideal independent voltage source is the one of which internal resistance value is equal to 0. But in practice it is impossible. How you can say the quality of your practical independent source? How you can say that quality? Quality depends on what? It depends on this value. If it is small values, if the Ri is in the range of 1 or 2 or 5 ohms, these are small resistance values. If it is in this range, it is good quality. If it is 200, as we calculated here, the quality drops, you see. It drops. So if you are producing a practical independent sources like that, batteries, so you've got to make this Re value as small as possible, then the quality is higher. What else I can say about that? So it says when you make it short circuit, so D and E, so you do it yourself, I'm going to leave it to you, but it is based on this. If you make a short circuit here, because of that, there's going to be a current pass through. But if you make a short circuit here, there's going to be very high current value, isn't it? Because let's say this, when it is short circuit, its resistance could be 1 ohm. If it is 1 ohm, the current that passed through here is going to be very high. But in here, it's going to be limited depending on this Ri value. So that's why there's going to be a different list too. And this is related with the quality of your independent source available in the market. We call it practical independent source. So that is the end of this example.